Okay, so we're now returning to stats. So this is chapter 6, and the first thing in chapter 6 is discrete random variables. So just before we look at some examples, we'll just go through some basic definitions about what random variables are. And this is really quite interesting because discrete random variables are used to model things like lightning intensity. So if somebody wants to predict how intense a lightning strike is going to be, or indeed how many times lightning is going to strike, then there's a certain random variable. There's something called the Anderson-Erickson function, I think, which kind of is used to model lightning intensity and to make predictions about things to do with when lightning is going to strike. So, first of all, a random variable is just a variable, something we can measure, whose value depends on a random event. So, the prototypical example to have in mind is something like the score when a fair die is rolled, which could be anything from 1 to 6. So the variable, the thing we're measuring, is the score on the die, and the random event is the rolling of the die. So, and we usually use capital Roman letters for random variables such as x, y, z. So something like x equals score on a fair die when rolled is a common example of a random variable. Okay, and the range of values that a random variable can take is called the sample space. So we've seen sample space before. In the context of probability, we've made sample space diagrams to illustrate all of the possible outcomes. So, the variable's random if the outcome isn't known until after the experiment's carried out. Another important definition is what it means for a variable to be discrete. As I'm sure you already know, it means it can only take certain values. So, for example, integers or half integers. The continuous analog of everything we're going to do is a bit more complicated and is in one of the further maths stats modules. So we'll see later that everything to do with probability in this topic basically amounts to summing up the probabilities of different things happening. If the probability is given by some continuous function, the continuous analog of that, where the variable can take any value, any real number value, involves integration, basically. So calculus is used a lot in probability. Okay, so, and then we need to say what a probability distribution is. So a probability distribution just describes the probability of the different possible outcomes in the sample space. And a probability distribution is called uniform. Maybe I should make clear which words I'm defining. There we go. So it is called uniform if all events occur, if all outcomes occur with equal probability. Okay. So, and again, the typical example of a uniform distribution would be the scores on a fair die when it's rolled. Because it can only land on 1, 2, 3, 4, 5, or 6, and the probability it lands on each of those values is 1/6. And so now we need to talk about how we're going to describe probability distributions. So there are a couple of ways we could do it. So if x is the score on a fair die, and so the different values x can take are 1, 2, 3, 4, 5, 6. So one way we can represent the probability distribution is to have a little x, which is the value 1, 2, 3, 4, 5, or 6, and this capital variable, this capital X, which is the variable, that's the score, and then we're looking at the probability that this variable is equal to each of these values little x. So this thing here means the probability that our variable, capital X, is equal to a given value, little x. Okay, so we know for the fair die, each of these is 1/6, because the distribution is uniform. Okay, so this is one way to represent it as a table. A different way is I could write it like this. I could say the probability x equals little x is 1/6, where x belongs to the set 1, 2, 3, 4, 5, 6. So this is a perfectly valid way of also representing it. This is something called probability mass function. So this way of representing it is called a probability mass function, or PMF. And in general, we could be a bit more precise about what a probability mass function is. We don't really need to know it as such, but it's a function P from the sample space, which I'll call omega, to the interval 0, 1, because probabilities are always between 0 and 1, such that for any event, so it's a function, such that for any event A in the sample space, the probability of A is the sum of the probabilities that x is equal to little x, where little x is in A. So little x are, if you like, all the different possible numbers in this event A. So this event A, in the case of a die, could be that the number it lands on is even. So then A would be the set 2, 4, 6, and then we'd sum the probabilities x equals 2, x equals 4, and x equals 6 to give the probability that the event A happens. So this, we don't really need this technical definition, but still, we've stated it anyway. And so some important properties that we do need to know are that probability of any event is always between 0 and 1. That's for all events A in the sample space. And also the sum of all possible outcomes has to be 1. So for all possible values x, the sum of the probability that x equals little x has to be 1. So this capital sigma we've seen before means the sum, but this is just saying the sum of all different probabilities is equal to 1. So these two properties are important. We do need to know these. Right, so now what we're going... Oh, just quickly, just one last definition before we do some examples. Just because it'll be useful later, is the cumulative distribution function, or CDF, is slightly different from this function p, probability mass function. This is a function f, again from the sample space 2, 0, 1, but this time it's defined by f of, if omega is this time described by all the different possible values that little x could take, we define f of x as the probability that capital X is less or equal than little x. So this is a cumulative function of all the probabilities up to and including little x. So again, for a die, we would have something like f of 3 is the probability that the score on the die is less or equal than 3, which would be a half. Again, this is not so important, but we're going to do some stuff with cumulative distributions later, so later in the chapter. But this is just a kind of formal definition of it. Okay, so now we're ready for some examples. So let's start with the first example. So we've got 3 fair coins are tossed. And the question is, part A, write down the sample space. So that's the set of all possible outcomes. Part B, write down the probability distribution write down the probability mass function for the random variable x, which is the number of heads. Okay, so first of all, the sample space, the space of all possible outcomes. Well, what different things could happen? We're tossing 3 fair coins. We either get heads or tails. So if we just toss 1 coin, then either we get heads or we get tails. If we toss 2, there are some more outcomes. We could have heads twice, or tails twice, or heads tails, or tails heads. If we toss 3 coins, then we're going to get the answer, which is, so I write it as a set just because sample space is really a set. We could have heads 3 times, or we could have heads twice and then tails, or we could have heads the first time and then tails heads, or heads tails tails, or tails heads heads, or tails heads tails, or tail tail head, or tail tail tail. Okay, so these are the 8 possible outcomes, and obviously for 4 coins there would be 16 possible outcomes. And then we're asked to write down the probability mass function. So perhaps first let's think about it in terms of a table. So if x is the number of heads, if we were to make a table like this, well, how many heads could we have? We could have 0, that's the tails, tails, tails case. We could have 1, in this one, for example. We could have 2, like tails, heads, heads, or we could have 3. So the probability we have 0 heads is just this one out of 8. They're all equally likely, so that's 1/8. 1 head, how many times does that come up? So I'll do that in blue. So we get 1 head here, and here, and here, and that's it. So that's 3/8. How about 2 heads? Well, again, if I do this in green, we've got 2 heads in these 3. So again, that's 3/8. And then lastly, the only one where it's 3 heads, that's 1 out of 8. So this is, as a table, the probability distribution, but we're asked to write down a probability mass function, the PMF. So we need to write this down as a function. So we've seen piecewise functions when we did the modulus function. So we can write this down as a piecewise function because there are 3 possible things that could happen. It could be 1/8, 3/8, or 0. is 0, obviously, when x is not equal to 0, 1, 2, or 3. The probability x is 7 is 0, because it couldn't be we get 7 heads from tossing 3 coins. So it's 1/8 if x is 0 or 3. It's 3/8 if x is 1 or 2, and it's 0 otherwise. And this is the probability mass function. Okay, so now we'll move on to the next example. So this is example number 2. So we're given a biased four-sided die. So I actually have a four-sided die. I don't have it with me here, but maybe I'll bring it in one day and show you, because I have a collection of dice with different numbers of sides that are quite interesting. So a biased four-sided die, it has faces numbered 1, 2, 3, and 4. X is the number on the bottommost face when it's rolled. And we're given that the probability x equals little x is k over x, where k is a constant. Okay, and then we're asked to find the probability that 1 is less or equal than x is less than 3. So, now, first of all, the first thing that's kind of a trick in this question is that you might be tempted to find your answer in terms of k. But that's not enough. That's not what they want you to do. They want you to give a numerical answer, because actually k is something you can work out. How do we know that? Well, if you think back to this thing here, the sum of all probabilities is equal to 1. So any question in this topic that has some unknown constant k, even if the question doesn't ask it, it's pretty much guaranteed you're going to have to find that constant. And the way to find that is to add up all of the different probabilities. So let's think. It can either be 1, 2, 3, or 4. If x is 1, we get k over 1, which is k. If x is 2, we get k over 2. If x is 3, k over 3, and if x is 4, k over 4. These are the only possible outcomes. So if we add up all of their probabilities, it has to be equal to 1. And then we can solve this. This is a linear equation in k. So if you add these up, I think you'll get 25/12, which tells us that k is 12/25. So we found the value of k. Now let's actually do the question. The question says, find the probability that x is greater or equal than 1 and less than 3. So if x is between, well, it can be equal to 1, so it could be 1. Can it be 2? Yes, it can, because that's greater than 1 and less than 3. Can it be 3? No, because this is a strict inequality, so it doesn't include 3. So we just want the probability it's 1 plus the probability x is 2. So we've got the probability 1 is less or equal than x is less than 3, is the probability x is 1 plus the probability x is 2. So the inequalities, whether it's strict or not, matters. So now, what's the probability x is 1? Well, let's go to the table. It's k. So this is k. What's the probability x is 2? It's k over 2. So we can see this is 3k over 2, and k was 12/25. So this turns out to be 18/25. So 18/25 is the answer. And now we'll just do one last example. So this is example number 3. So this time a spinner is spun until it lands on red, or has been spun 4 times in total. And the question is, find as a table the probability distribution of the random variable S, the number of times the spinner is spun. Okay, and then just to give a picture of the spinner has 5 sections, so it's supposed to be a circle, which I'll attempt to divide into 5 equal pieces, and 2 of them are red, and the other 3 are blue. Okay, and the question is asking us for the distribution of S, the number of times it's spun. So either it has to be spun once. So the first time it's spun, when would we be done? When would we stop spinning? Well, we spin until it lands on red, or it's been spun 4 times. So if it lands on red straight away, that's it. There was only 1 spin. If it doesn't land on red, we'll keep spinning again until either we land on red or it's been 4 times. So the probability S is 1 has to be the probability of red, which is 2/5. The probability S is 2. Well, how could S be 2? The only way we spin twice is if the first time is blue and then the second time is red. So this is the probability of blue and then red. So that's equal to 6/25. What's the probability S is 3? Well, the only way S could be 3 is if the first 2 times are blue, and then the third time is red, because we stop spinning when it's red. So this is blue, blue, red, and then if we work this out, this is the previous answer times 3/5. So this is going to be 18 over 125. And then what's the probability S is 4? Well, we have to stop spinning when it's been 4 times. So this is going to be 1, take away the other 3 numbers. So it's 1, take away everything we've just worked out. And if you work that out, you're going to get 27 over 125. And then we're asked to give it as a table. So the table is going to look something like this. We've got little x, or we could use little s, and then the probability capital S, the variable equals little x. It's either 1, 2, 3, or 4, and then we just fill in the relevant probabilities. Okay, and that's the answer. And so that's discrete random variables. Both examples 2 and 3 are common kinds of questions that come up in the exam. So those are standard techniques to learn. And if you ever have an unknown constant k like this, most likely you're going to have to find it.